talk about replacing conditionals with polymorphism and primitive obsession. Or expressed in a different way, the limits of replacing conditionals with polymorphism. In other words, as far as I understand it, it seems that it's not always possible to replace conditionals with polymorphism. Let's talk about when that is. But let's first make sure that we are on the same page with the concept. So, replace conditional with polymorphism is a phrase that was popularized by Martin Fowler in his great book, Refactoring, as a programmer. I find that this book is one of these go-to books that every programmer must have. I've linked it in the description. Be sure to check it out. Moving on. So yes, the term is popularized by Martin Fowler, but what does it actually mean? Let's break down the statement. We're talking about replacing conditionals with polymorphism. This means that we need to understand what conditionals are and what polymorphism is. So conditionals are if statements, switch statements, etc., etc. When you're switching, right? When you're saying that there are multiple paths through this program, when you're making a branch in your code. Polymorphism, on the other hand, polymorphism is, if I'm not mistaken, a way of achieving dynamic dispatch. By example, it's when you have an animal as a superclass, or as an interface, or as an abstract class, and then you have a cat and a dog, both inheriting from animals. The point being that the rest of your code can then couple itself to animals, rather than to concrete cats or to concrete dogs. Self to a superclass. You couple yourself to interfaces rather than concretions. But if you're watching this channel, I'm pretty sure you're already intimately familiar with polymorphism, so let's move on. The point here is that we're saying replace conditionals with polymorphism. So every time you have a conditional, you should replace it with some kind of polymorphism. The easiest way to get it is probably to think about the example given by Martin Fowler. I've linked that in the description. But essentially, the part where he replaces conditionals with a polymorphism is that he has some kind of movie database system and he gives genres to movies. So he puts enums in the movie class. So he has a class that represents a movie, and the field in the movie class is the category of the movie or the genre of the movie. And instead of having some kind of class, he simply uses an enum or an integer or something like this. I can't remember, but essentially some kind of primitive or primitive-like thing that represents the category that that movie belongs to. Actually, when I think about it, it's actually not genres, but it's something like genres. But whatever. Essentially, the point is that he starts out with this as a field and then moves towards instead making multiple types of movies where the movie type represents what kind of genre it is. Again, I'm saying it incorrectly. I'm saying that it's genre. It's not actually genre, but I think you get the gist of it. The reason we're saying replace conditionals with polymorphism is that when we are now grabbing out something or calculating something that depends on what type or what genre a movie is, instead of switching, instead of reading this enum or integer or whatever it was, reading this primitive and then making a decision based on that primitive, we can simply dispatch into the class. And then because of polymorphism, depending on which actual concrete type it is of, you can calculate different things. I'm probably making it overly complicated when I talk about it like this. If you just think about it, it's actually super trivial. If you have dog and cat and animal, and if cats and dogs override the speak method from animal, then if you're passing around instances of cats and dogs, mixing them, but refer to them as animals in your code, then as soon as you call speak, you will call the method on the cat if it's cat, and you will call the method on a dog if it's a dog. Essentially, dynamic dispatch. So now we've handled what replacing conditionals with polymorphism is. So before we dig into the limits of that, let's first talk about primitive obsession. So primitive obsession is the phenomenon where a programmer is overly committed to coupling to primitives rather than complex objects. So again, let's define, right? Like, what are primitives? Obsession I won't define because I think you can figure out what that means, but primitives essentially are primitive obsession means that a program is overly obsessed with passing around primitives rather than passing around objects defined by the program. So instead of passing around said animal, for example, and then calling speak on that instance, for example, I may be first extracting the string of what the animal says and then pass around that string. So in some oversimplified sense, it's a way of extracting data out of objects, extracting the primitive data out of objects, and then passing around that instead of passing around the complex objects. We'll talk more in depth about this phenomenon some other time because it's super interesting and there are some nuances, and one could ask why this perhaps isn't a good thing because primitives should probably have less dependencies. But it's not as obvious as might think. Let's talk about this some other time. But essentially, here's where I end up. Primitive obsession may seem like a good thing at first, but when you start to think about replacing conditional with polymorphism, you'll realize that you can't replace conditional with polymorphism if you have primitives. You can't use polymorphism if you have primitives. So essentially what you're doing is that you're forcing yourself into a place where you have to switch, where you have to use switches, where you have to use if statements, where you have to use conditionals in order to handle branching of the program. Instead of, if you had objects, you could use polymorphism, which in many ways is a much more sane way or safe way to handle switching, to handle conditionals in your program, or rather to handle branching in your program. So what I find super interesting about this is that after having been a fan of replacing conditionals with polymorphism for a while, I started to think that actually maybe we don't even need conditionals at all because we can always replace conditionals with polymorphism. And actually, if I'm not mistaken, the object-oriented language Smalltalk doesn't even have the if construct. Now Sandy Metz shows in another talk, I've linked it in the description, that you can use other constructs of the Smalltalk language to build what's essentially an equivalent of the if construct. But again, it's kind of a thought-provoking idea to say that actually the language doesn't need a dedicated construct for conditionals. But here's where it gets interesting. I like to think of this in terms of the edge of the application. When we start to hit primitives, when we necessarily have to hit primitives because of the requirements of the application, then we can't use replace conditionals with polymorphism. Then we can't replace conditionals with polymorphism. So at the edge of our application, there is some dirt that necessarily has to be there because we can't encapsulate it into our nice domain objects and into our nice domain language. And if you think about it, just let's take a concrete example to make this more concrete. Think about something trivial. Let's say you are building a console application, a terminal application, and the user is prompted to type in a number from 1 to 5. You get it in as a string because it's a terminal application, and you want to take different paths in the program. You want to do different things depending on whether it's a 1, whether it's a 2, whether it's 3, etc., etc. And if it's something below a 1, or if it's something above a 5, then that would be incorrect input and you want to do something completely different. So for all of these scenarios, we have different paths through the program. So somehow we need to identify which number the user actually pressed and then move the program accordingly, or direct the program accordingly. And while I haven't given this deep thought, if you just think about it spontaneously, you realize that, well, of course you could probably find some kind of way to define that particular domains of numbers belong to a particular type, right? But I'm not necessarily sure how that's better than conditionals, right? As long as you are isolating your conditionals to the edge of the application. So essentially my point is, to sum up, if your requirements necessitate the use of primitives at some point in your program, then at some point in your program, you will have to use conditionals. You can't replace the conditionals with polymorphism because the requirements inherently necessitate the use of conditionals. Because we are hitting the edge of the application, we are hitting a point where you get data in a format that is not controlled by you in terms of a primitive. And again, I haven't thought about this deeply, but probably this holds for example, API calls as well. This is why I'm saying the edge, right? It's not necessarily just the concept of primitives. It probably also goes for exiting the boundary of the application. So interacting with third-party libraries, interacting with the user, etc., etc. As soon as you are leaving the land of your nice controlled code and get into the wild, right, things are structured in a way you don't have control of, and thus we may be forced to actually use conditionals. But as long as we're in the boundary of our own application, I see no reason why we should ever have to use a conditional. I mean, the conditional will have to stem from primitive obsession. Finally, before I go, let me just formulate this as a design tip. The way I'm thinking about this is that if you understand that a particular requirement necessitates the use of a conditional, then you should isolate that conditional in one place, and you should push it as far as possible out to the edge of your application. You should not spread out this conditional throughout, scatter out your conditional throughout your application, and you should not let it sink in deeply into the core of your application, but rather you should push it out to the boundary, right? You wrap it in some kind of wrapper that's wrapping some kind of wrapper, etc., etc. Like, you make sense of the conditional within your own domain language. So to me, it kind of sounds like a way to handle necessary errors. There's something problematic you need to handle, so you wrap it in something that's nicer and hide it. You treat the conditional as a deceive, right? You're isolating it into a particular place of your application, pushing it as far out so that it's not something that you use often, instead of letting it spread out through your application, because as Sentiment says, conditions tend to breed. Thanks for watching. Remember to subscribe, and I'll see you in the next one. Here's something brief for those of you who are interested in when to use mockist style testing and when to use classicist style testing. So here's what I want to say essentially. If you don't know the outcome, you have mock. Expressed in a different way, when results are emergent, you have to use mocking. If you're not familiar with the differences between classicist style testing and mockist style testing, or integration testing versus unit testing, then I highly suggest you check out my 2 other videos on those topics. I've linked them in the description. But moving on, here's the argument. In classicist testing, or integration testing that aren't mocking the boundaries, you essentially have to know the outcome of any particular interaction in order to test that interaction. Of course, that makes perfect sense if you think about it. The whole idea of integration testing is that you have one unit under test, and given some global state, or a set of particular members that you pass it, you expect a certain result. So if you think about it in terms of the classic prepare, act, assert, you are preparing some kind of state, making some kind of action, and asserting that you get a particular outcome. And if you don't know what the outcome is, then what are you supposed to assert? Now I understand that having an outcome that is unknown may sound like a contrived example, and may sound like something that doesn't happen. So let me give you a concrete scenario. So I work with agent-based modeling, and in agent-based modeling, the whole idea is that we are looking at emergent phenomena. But what does emergent phenomena mean? Essentially it means that we know the micro-interactions, but we don't know the macro outcome of these micro-interactions at scale. Now I won't dig into the depths of agent-based modeling, let's do that some other time in case you're interested. But essentially the point is that we know the processes of some things. We know how some particular things interact with each other, but it's not necessarily known what the result of a series of these interactions will be. What I find particularly interesting is that this is not necessarily a question of non-determinism. It's not necessarily a question of that the interactions are non-deterministic. So it's not necessarily a question of that the results of the interactions are impossible theoretically to be calculated, but rather it's a question of that calculating the outcome might be significantly tedious or infeasible. So if you think about that, I assume that actually makes sense. So if you have lots of dependencies, or if you have lots of interacting objects, at some point it's going to be very difficult to calculate the outcome. Think about, for example, the classic physics three-body problem, where you in space have 3 bodies that exert gravitational forces upon each other, which leads us to a situation where calculating the positions of these 3 bodies after a long period of time becomes very tricky, if not to say infeasible, simply put because of the butterfly effect. I'm sure you've seen that movie with Ashton Kutcher, right? A butterfly flaps its wings in one end of the world, which causes an earthquake at the other end of the world. Essentially, you're dealing with highly complex systems, then the effect of a small change might be non-linear in the sense that the effect of a small decimal change might be massive in a different location because of all these small interactions. Which again, in the case of agent-based modeling, puts us in a situation where we, yes, can calculate the outcome of a particular set of interactions, but it's possible that we don't actually want to because of the infeasibility. It's possible that we don't actually want to because it will take serious amounts of time to figure out these calculations. And if we later down the road change some of these small parts, i.e. The butterfly flapping its wings, then the outcome will be completely different, which means that all our tests will be wrong. So instead, we simply use logic. Instead of doing classic integration testing, instead of using real dependencies, we just check what we know. We check that the different objects are interacting with each other according to specification. So to sum up, if the outcome is emergent, if the outcome is unknown, then it may be preferable to use mocking rather than classicist testing, rather than integration testing. It may be preferable to mock all of the boundaries and check that we are composing objects correctly, check that the interactions are working correctly, that all of the units behave correctly in isolation, and that they are composed together correctly, rather than doing classicist testing, rather than doing full integration testing. That's it. Thanks for watching. I'll see you in the next one.
I write a lot of things for school, but I also write sales descriptions for my Etsy shop.
I use Grammarly on my work emails and also on my cooking blog.
Grammarly is a game changer for me at work. I also love it for social media posts. I connect with candidates on LinkedIn. My tweets.
Message boards.
My resume, cover letter.
I write superhero fan.
You've probably heard a lot of people say that downcasting is a cold smell. I'm one of those people, so let's talk about why that is. So downcasting is a form of typecasting. And typecasting can roughly be said to be the idea of taking an instance of one type, but treating it as an instance of another type. Roughly. So typecasting is not specific to object-oriented languages, but downcasting and upcasting are usually found in languages that support hierarchical data types, or polymorphism. But before we push on further, let's be sure we are on the same page on what downcasting and upcasting is. So let's do a classical animal example. Let's say that we have an animal superclass and a cat subclass. Cat inherits from animal. So if you have an animal, but you treat it as a cat, then that is downcasting. If you have a cat and you treat it as an animal, then that means it's upcasting. So in that sense, it's very simple. Downcasting casts down the inheritance chain, and upcasting casts up the inheritance chain. And up means up towards the superclasses, and down means down towards the subclasses. We'll talk about upcasting some other time, but let's now focus on why downcasting is considered a cold smell. So if you think about the animal example that we just talked about, the problem should become quite apparent to you if you just think about it again. Think of it this way. Given the system that we've designed, every cat is definitely an animal. But not every animal is definitely a cat. Think about it. Every instance of a cat definitely has to be an animal. But given any instance of an animal, you cannot be 100% certain that that particular animal is also a cat. Because cat is a subclass of animal, which means that hypothetically, the system could contain even more subclasses that are also animals, and thus we have uncertainty. Of course, in the kind of silly scenario that I posed, we didn't actually have any other subclasses apart from cat. So in our system, we could in some practical sense actually be 100% certain that every instance of an animal would be a cat, for the mere reason that we don't have another subclass that inherits from animals. But remember, as always, we're designing systems, right? We're architecturing systems. And I'm not saying that you should anticipate requirements that you're currently not anticipating. But what I'm saying is that if you use that kind of logic, I think it's fairly certain to say that you're going to be in a world of hurt a lot of times. So let me put it in a slightly different way. In some sense, I'm shocked that the idea of downcasting actually exists in serious languages that we use, such as C# or Java. If there is some kind of rational idea behind this, please feel free to outline that or point me towards some resource in the comments. Because honestly, I really haven't found any good reason, but I may be wrong. However, the object-oriented language OCaml doesn't support downcasting. So at least some people seem to agree with the idea that downcasting simply isn't ever a good idea. And in case I'm underestimating the amount of people that think that perhaps we have downcasting in a lot of languages for legacy reasons. Perhaps people, when designing these languages, didn't realize how fundamentally insane downcasting is, put them in the languages, and people start using them. And then now we have code bases where people are using downcasting, and then we simply just keep it there. But I mean, now I'm totally speculating. I have no idea. So with the arguments that we've looked at, I'm pretty sure you already agree that downcasting is in some sense kind of insane. But to put one final nail in the coffin, let's look at one more example. Just think about the absurdity of this scenario. Assume that you were building a class, you were writing a class, we're on the same team, you and I, right? And you were writing a class, and in the constructor of that class, you take something that is the type, say, an animal, but then in your constructor, or later sometime in your code, you are downcasting from an animal to a cat. And then you give this class to me. And if you think about this situation from a contract perspective, right? As in, from an interface perspective, as in the boundary between me and you. So the way I interface with your code and the way you interface with my code. I mean, trying to find some agreements on interfaces is like 101 of actually trying to produce some useful entity. So from an interfacing perspective, essentially what you're saying to me is that here's a class, you can use it the way you want, as long as in the constructor you give it an animal, right? What you're saying is that anything that is of type animal is okay. So I make that assumption. I take your class, I instantiate an instance of your class, and I pass something that is of type animal to the constructor. But what happens? It blows up. Because in your code you were downcasting. You were downcasting to cat, and maybe I sent a dog. Right? Your contract said you want an animal. I instantiate an animal, a dog that inherits from an animal. I pass you the dog, and then your code blows up because you were downcasting to a specific type. And then you may argue, okay, wait. But I could have used this instance though. I could have checked whether the thing I'm passing is of type cat, and then only in the case that it is of type cat, then you downcast, right? And you're right that that would cause an exception, but design-wise, this is insane. I won't dig into this argument in depth. But please see my other video on why type checking is a code smash. If you think about it, what's happening is that we are breaking the open-closed principle. The open-closed principle says that something should be open for extension, closed for modification. So your class, through dependency injection, is closed for extension, not only for modification. Because when you are typecasting to a cat, you're suddenly locking me in. You're saying, okay, if you pass me something that's not a cat, then there are certain parts of the behavior of this class that you won't get to experience because it's only for cats. But that's insane. And the interface should be that you're expecting cats, and only cats, and not animals. So with that said, I'll be quiet. Essentially, my point is this. I don't think there is ever a valid use case for using downcasting. It's just fundamentally insane. The idea of downcasting is completely backwards, completely insane. But if you have an example of where it does make sense, please shoot that in the comments and we'll discuss. But please avoid discussions of pragmatism. Because if you're arguing pragmatism, then I would spontaneously argue that the cost of not downcasting is so silly low, it is so low that it's just silly to argue that it's pragmatic to use downcasting. But apart from that, if you have any good arguments, I'd love to hear them. That would be fantastic. Anyways, thanks for watching, and I'll see you in the next one. There's this interesting talk by Robert C. Martin where he talks about how we as programmers perhaps should approach our occupation a bit more like doctors approach theirs. So the scenario is as follows. If you think about how software is becoming increasingly important and embedded into society, we have software in streetlights, cars, planes, schools, projectors, TVs, watches, smartphones, coffee makers, etc., etc., etc. Software is slowly finding its way into every part of human life. And the problem with this is, of course, that as we all know, there are bugs in almost any software. The problem is, of course, that if you have a safety-critical system, if you have a car, if you have a plane, if you have some kind of heavy machine, then a failure in that machine could actually cause, literally, death. Or even if not death, it could cause serious infrastructure damage or environmental damage. As you can see, if you start to think about this, this is increasingly becoming a very, very real problem. So while I don't remember all the details of Robert C. Martin's talk, essentially his point is that we as programmers should start to think about forming some kind of organization whose intent is to protect the interests of honest supposedly a few programmers were behaving recklessly, and as a result of that, actually caused damage. So the way I understand it, what he's saying is that programmers who behave recklessly in the name of programming should not be allowed to be called programmers. So if you think about doctors, for example, doctors have licenses, or psychologists have licenses. So if you behave recklessly, then you lose your license to practice your practice. And just to sort of contextualize this argument, the way I understand it is that he is actually concerned that if we as programmers, right, as part of an occupation, as part of a craft, do not take care of the situation or start to show that we are able to handle this situation systematically, collectively, then he's afraid that governments will step in and handle this for us through regulations or some other means. Now, whether that's a good thing or bad thing that the government steps in, you have to decide on your own. Now, I'm from Sweden, which is a country with a very strong government, which allows us a lot of benefits. So, of course, I wouldn't necessarily say that it's a bad thing that the government steps in. But then again, from my perspective, it's good to ponder the possibilities that we have in case we can find a better solution. Now, before we get into the argument that I want to make in this discussion, let me just make it very clear that I think this idea of having a license in order to control who's considered a professional, a responsible programmer, I think that idea is excellent. It's a very, very good idea. But I have one nuancing point that I would like to bring into this discussion in order to avoid some potentially unexpected but definitely unwanted consequences. Let's talk about those. There is a great book by Matthew Seed. Sorry, I don't know his name, but the link to the book is in the description. The book is called Black Box Thinking. And we're not meaning black box as we talk about in software, we talk about black box, white box. We mean black box as in the little black box inside an airplane, you know, the sort of indestructible box that when an airplane crashes, you can dig out the plane wreckage and then listen to the recording in the black box in order to figure out what actually happened. And consequently, here's the key point, learn from that mistake. So the interesting point that this book raises is that it's very important, whether we consider a mistake in the organization and the company and in the industry as the mistake of any particular individual or as the result of a series of interconnected events which cannot necessarily be blamed on any particular individual. So the point is to try to separate obvious malicious intent from accidents. The argument being that there is the risk that if we start to blame systematic errors on individuals, then individuals may start to hide information because they fear being convicted or blamed. In other words, suffer the consequences of what is supposedly their mistake, but in actuality perhaps not actually their mistake. So Black Box Thinking is a book that discusses this distinction at length. Essentially, it reports a bunch of case studies or anecdotal examples from both sides. So to very briefly summarize the book, the way I understand it, it seems to me that the main point of the book is that if you look at the two industries, healthcare, in other words doctors, and aviation, in other words flying airplanes, then aviation has been sufficiently more successful in collectively learning from their mistakes than doctors have. And the argument is that this has to do with, or this is because, aviation do not easily blame individual pilots for accidents. Do not easily blame individuals, put the blame on individuals. They do not seek scapegoats to the same extent when an accident happens, as the healthcare industry does, or as doctors do, or as hospitals do. So in other words, when a mistake is uncovered, when an accident happens, then the system is analyzed in terms of trying to identify what the context was in which the error actually happened, in which the mistake actually happened. So in other words, the thinking sort of goes that in order to understand and learn from this, in order to mitigate this issue in the future, we need to understand all of the details that led us to this particular event. In other words, one is not saying that a particular individual was sloppy or was careless. To a certain extent, of course, because, again, the point is to differentiate deliberate carelessness or malicious intent from mistakes that involve more individuals. In other words, think of it this way. I don't remember how to translate that expression into English, but you know the expression that if you have a bowl of water, then the last drop of water that makes the bowl of water overflow, right? That doesn't fit into the bowl, right? It's kind of that type of analogy. In other words, we're saying that it's not only the last drop if the bowl is overflowing. It's all the drops' fault, right? Or at least we need, in order to understand and mitigate, we need to look beyond the last drop. And it's not necessarily only the last drop that was the problem, and even if we would solve the last drop, that wouldn't necessarily be the most efficient way, effective way of dealing with the particular issue. So again, the book argues that healthcare doctors have been more focused on blaming individuals, which have led to work environments where individuals are resistant towards reporting mistakes that they or their colleagues have conducted. Why? Well, because they run the risk of being questioned, held accountable for the effects of that mistake. Right? If you could potentially use your license, then regardless of how honest you may be or feel that you are, it may very well be that you choose to hide information, either deliberately or by simply not reporting. And again, from an individual's perspective, this isn't necessarily a bad thing. But from a collective perspective, from the organization's perspective, or from the industry's perspective, it's a catastrophic thing. Because we're trying to learn from our mistakes so that we can deliver the best possible service to our clients. Right? I mean, think about the airplane industry. We want airplanes to not crash. Right? So as a customer of airplanes, I would very much want the aviation industry to have control over their mistakes and learn from their mistakes so that they're not repeating the same mistakes over and over again. Right? Of course, I never want to be in a plane crash, but at least if I am in a plane crash, it would be in some sense good if that was because a new, completely unseen error has occurred, rather than an error that has occurred 50 times already, but nobody has chosen to report them and learn from those mistakes. So back to software. Back to the license to code, right? Why am I talking about this in relation to Bob Martin's talk? Here's the thing. Again, I think it's an excellent idea that he's proposing, but I think it's very, very important that we avoid turning into a blame culture because of these outlined reasons. If we turn into a culture where programmers are solely blamed for the mistakes that they perform, then over time we may not necessarily learn from our mistakes as an industry. So when accidents related to autonomous cars happen, for example, of course it would be super important that we collectively learn from this and derive information so that these accidents won't happen again. But in a blame culture, it's very unlikely that we will actually learn from these mistakes because it's very unlikely that the information of the mistake will surface in the first place. Of course, until the accident happens. And when the accident happens, everybody's fleeing because nobody wants to be turned into the scapegoat. So to make it a bit more clear, what could actually be a systematic error, right? Or an error that stems from the interaction between different pieces rather than solely an individual's mistake? Well, think about the pressure we experience as programmers, right? There's always this sort of tension between delivering in time and delivering something that's good. We're always pressured to deliver as quickly as possible, of course, right? It's a strictly economical issue. But in order to play it safe, in order to deliver safe systems and stable systems, we usually need to spend more time. But the time is money, so there's this tension. And this is just last. There are tons of aspects that you can think about, where if you start to dig down, you'll realize that there are many individuals involved in the story of any particular accident. So to round this up, let's talk about what I think we should do. Essentially, it's this. I think it's very important that as we move towards this new world of software everywhere, and as I hope, move into some kind of license to code, I think it's super important that we try really hard to differentiate between deliberate malicious intent and systemic faults. As it's very, very important that we do not turn into a blame culture. If we are to survive, if we are to avoid accidents in this world of software everywhere, we need to collectively learn from the mistakes that we inevitably will make. And remember, think about the future carefully. I mean, this is not about small, trivial errors that have no severe consequences. We're talking about serious environmental damage, infrastructural damage, economical damage, and of course, the risk of people's lives. It sounds alarmist, and I'm not intending to be alarmist, but I just really hope that we can approach this issue seriously, because software will inevitably play a very, very serious role in the society that we're building. So before I go, I just want to mention again that the book black box thinking is actually super good, and I highly recommend that you read it. I put a link in the description. And remember, I listened to it as an audiobook, and if you're not already a member of Audible, then you can get the first book for free. So essentially, you can get this book for free if you're not already a member of Audible. I put the links in the description. So those are my 5 quick cents. I've also linked the video by Robert Martin in the description, so be sure to check that out. It's super interesting. Thanks for watching, and I'll see you in the next one.
So I've got my essay written, and I've been working on it for about a week. So now I'm going to show you how I use Grammarly to edit.
The fact that language is statically typed does not necessarily entail that the language is explicitly statically typed. I just want to quickly talk about that today. We'll dig deeper into the depths of static languages versus dynamic languages some other time, because there is some interesting depth there, but that's for another video. Today I just want to say that static typing does not entail explicit static typing. So let's get straight to what we're talking about here. We're saying that there are 2 dimensions. We're saying that there is explicit versus implicit, but also that there is dynamic versus static. So if we think about these properties, then that means that we could sort of draw a quadrant diagram where we have 4 different combinations. We have explicitly statically typed languages, implicitly statically typed languages, but also explicitly dynamically typed languages and implicitly dynamically typed languages. So this is the way I thought we would approach this spontaneously, but then I realized that perhaps explicitly typed dynamic languages probably doesn't actually make any sense, so we'll talk about it in a different way. But let's first get these categories straight. What does explicit versus implicit mean, and what does static versus dynamic mean? So for the purposes of this video, we can think about static versus dynamic as in that a language that is statically typed enforces types before the program runs. So in a compiled language, it enforces types at compile time and not at runtime. Whereas the dynamic language enforces types at runtime. In other words, you won't know that you have a type error before you actually run the program. And also remember that when we're talking about types, we're talking about the types of things, such as the type of a variable or the return type of a function. So a type in this case is a string or a boolean or an integer or a double or object or any of your customly defined types, etc., etc., etc. So what does explicit versus implicit mean? Well, explicit simply means that you explicitly state the types, whereas implicit means that you are not stating the types, that the types are implicit. In other words, if you put a literal 1, for example, in a variable, then the static checker or the compiler could actually figure out on its own that thing is a number, for example, an integer, right? So if you would put 1 into one variable and 3 into another variable, and then you add these 2 variables together, then the static checker or the compiler would know that this is correct from a perspective, right? It infers the types. The types are implicit, but they can be inferred from the literal. We know that we don't actually have a type conflict. So if you think about that explanation, you can probably see why talking about the dynamically typed explicit language probably really doesn't make any sense, because then we're saying that the types are stated explicitly, but we're not actually enforcing types. So it makes very little sense to have these type annotations. But I may be incorrect about that. I haven't given it a lot of thought. So if somebody claims otherwise, please do let me know in the comments and we'll discuss that. That would be very interesting if it is so. So instead of thinking about this as sort of a quadrant diagram, right, where we have 4 different combinations, we can think of it as a tree. Right? First we decide whether the language is statically typed or dynamically typed. Right? Static and dynamic. Right? Then we decide whether it is explicitly typed or implicitly typed in the case that it is static. So we say, okay, is it a static language? Yes. Okay, if so, then is it explicitly static or is it implicitly static? Right? And dynamic is just dynamic. So let's talk about concrete languages. Dynamically typed languages are languages such as JavaScript or Ruby. Examples of explicitly statically typed languages are languages such as C# Java. And an example of a language that is implicitly statically typed is Haskell. So now we've only talked about 2 dimensions. We've talked about explicit versus implicit, and we've talked about static versus dynamic. But oftentimes you also see the notion strong versus weak. So I deliberately avoided to talk about strong versus weak, as apparently there is no actually formal agreed upon definition of the difference between strong and weak typing. So my loose understanding of this is that when it comes to strong typing, people are arguing that if a language is strongly typed, then the typing is enforced more stronger, essentially. And if it's weakly typed, it's enforced, but it's less enforced. It's more weak, right? But again, I think it would be very sensible, and it seems like there are a lot of comments saying that out on the internet, that it's better to avoid using they probably cause more confusion than they help us to sort things out, because there is no agreed definition of one. So let's stick to static versus dynamic and explicit versus implicit. So that's it. I just sort of wanted to scratch the surface and make sure that we all know that just because a language is statically typed, it is not necessarily explicitly statically typed. So when someone is asked what a statically typed language is, and they answer that it is when you write string or int or float, etc., in front of variables or in arguments and methods, etc., then that is kind of incorrect, because that would be an explicitly statically typed language. But what actually defines whether it is static or not is whether it enforces these types before the program is run. But again, we'll talk about static versus dynamic in depth some other time. Thanks for watching. I'll see you in the next one. Statically typed, explicitly typed static. Explicitly typed static. Examples of static. So, in the 1970s, this guy called Manny Lehman developed what is known as Lehman's laws of software evolution. We'll talk specifically about these laws in another video, but what I find particularly interesting is that Lehman said that these laws only apply to a certain type of systems. So he divides the systems into three categories: E-type, P-type, and S-type systems. And it's these categories that I want to talk about today. Because when arguing about different things, I find it really useful to remember which type of systems we are talking about. Because if one person arguing on one side is talking about one type of system and another person is talking about a different type of system, of course we're going to disagree, but we're not necessarily disagreeing in what we're arguing about, because we're disagreeing in the point of departure. We're talking about fundamentally different systems, which means that we probably naturally will disagree. So let's start with S-type systems. So S-type systems are systems that have well-known specifications, that have a well-known solution. So if somebody, for example, asks you to implement code sort or implement a particular mathematical function, then that has a known specification and a known solution. It is possible to exactly say whether the program is correct or not, and it is possible to implement a 100% correct solution. These are S-type systems, right? And as you can imagine, a very narrow scope of type of systems, right? Not a lot of systems that we're working with fall under this category. Moving on, P-type systems. P-type systems might actually have a specification in terms of what a 100% correct solution would be. There might even be a way of theoretically reaching that perfect solution. But in practice, it would be utterly infeasible to actually implement that solution. So this is when we oftentimes talk about heuristics. So a good example of such a system would, for example, be chess. If you want to develop an algorithm that plays chess perfectly, it is theoretically possible to construct the perfect solution. But in practice, if you would run that solution, as you can imagine, of course, the combinatorial complexity is way too high, so it is intractable. The solution is intractable. So you can't actually use that solution because your program will never be able to make a move because it's always thinking too long. And this is why we talk about heuristics. Heuristics is a way of saying, okay, let's apply some kind of knowledge, let's apply some kind of rules of thumb to eliminate some of these branches of the search tree. So as you can imagine, this brings in even more programs. So if your program can be either an S-type or P-type system, then we can talk about a bunch of more systems that we encounter in daily life. But let's now talk about E-type systems. So E-type systems are real-world systems. Systems that are intertwined with processes of real life, with business processes, with real people, where there is not necessarily a specification of 100% correctness, because it's ever-changing. We're not really entirely sure what we want to have, or even if we are sure what we want to have, we're not necessarily sure that what we want to have today is what we're going to have to want tomorrow. And again, it's important to emphasize that that's not necessarily just because of uncertainty, right? That's because it's operating in an environment that's subject to change. People's needs, the business needs might actually, for very good reasons, change over time, which means that the specification of our system is not stable. So to contrast this with P-type systems, think about chess again. If you're seeking an algorithm that plays chess perfectly, then that would be a P-type system. But if you're developing a game in which there also is an algorithm that plays chess, then that whole system is probably an E-type system. Because suddenly you have loads of other things to take into account as well, such as, for example, the user interface, what key combinations you use to interact with the program, how to boot the program, etc., etc. These are things that are non-stable in any real-world environment, usually. So the reason I think it's useful to know about these different types of systems is that in most of the environments where we are developing systems as programmers, we are actually dealing with E-type systems and not P-type and not S-type systems. So when people are arguing against things such as, for example, abstraction, we need to carefully listen to their arguments and consider whether they are arguing as if we were building a P-type or S-type system. Because if they are, then we are fundamentally disagreeing on a different level. We first need to settle that argument. We first need to agree that we are talking about type systems, and then realize that the notion of E-type systems is that they are, by their very nature, subject to change. We cannot be 100% certain about the specification. We cannot be 100% certain that the specification of today will be the specification of tomorrow, which I would humbly argue should lead us into thinking about our design, our architecture in a different way than if we were building P-type or S-type systems. So to sum up, in S-type systems, we can specify the program with 100% correctness. We can talk about the perfect solution of the program. The problem is well understood and the solution is well understood. But in P-type systems, the problem can be well understood and the solution can be well understood, but it's practically impossible to actually implement the perfect solution. So these usually turn out to be systems where we involve heuristics. And E-type systems, I like to think of the systems that we usually deal with on a day-to-day basis. Systems that are subject to change. Systems that solve problems that are deeply interlinked with social processes or social environments. So in some sense we can think of them as not being purely theoretical. That's it. Thanks for watching, and I'll see you in the next one. If I understand the open-close principle of the solid principles correctly, then I think in extension, or in its extremist form, it's saying that you should never have to rewrite any of your code. You should only write new code. You should never rewrite your existing code. You should only add new code to your code base. This is, of course, a kind of profound statement, and I understand that it seems unreasonable, but I assume that you also see that if you were able to do that, then it would be easier to avoid bugs in your code, to avoid problems that evolve over time. For example, you would never run the risk of changing a particular piece of code, thinking that it's not used somewhere else, and realizing that it's actually used somewhere else, and then breaking that piece. So I've been thinking a lot about this lately. I mean, how could you possibly never have to rewrite code? So let's talk about this beyond the open-close principle. Let's say that what we're trying to avoid is rewriting code. So let's say that the actions that we can do is that we can add new code, right? We can add new classes and modules, but we can also delete code. We can also delete classes and modules. This means that if you want to change something, you have to delete the old one and insert a new one. And we're not talking about chunks of code, right? Because again, chunks of code is risky. I think it becomes easier to think about if you think about dependency injection. This is possible through dependency injection. So instead of writing, for example, large monolith classes, and instead of instantiating your dependencies within a module, right? Instead of a particular module or class having to know about its dependencies, it instead takes parameters of types, where the types would be duck types, right? It instead takes parameters of types that perform particular roles. This means that if you need a new thing to play the role, you simply instantiate a new thing and inject that new thing into wherever you were using the old thing. And this is the key to understand how we stop rewriting code and instead only write new code. So if you think about it, it probably makes a lot of sense. If you have a sorting method, for example, Instead of hard-coding a particular sorting algorithm in that sorting method, you instead, in a functional language, you take a function, or in an object-oriented language, perhaps take an object that plays a strategy role. You take a strategy object that has a sorting algorithm, that uses a particular sorting algorithm. If you do that instead, then you can simply, if you want to change your mind later to a different sorting algorithm, you can simply inject another object, a different object that utilizes a different sorting strategy. Which means that at the point where you want to change your mind, where you want to change from one sorting algorithm to another one, then you won't actually have to rewrite code. You simply have to create a new sorting class and then inject that member instead. But if you're paying close attention, you would of course quickly realize that when I say inject the new one instead, that of course has to become a rewrite, right? Because yes, you create the new member that you want to use, but at some point you have to put that new member into the existing system, right? Into the existing object graph. And then it has to turn into a rewrite, or no? What's interesting is that even then you can avoid a rewrite by simply rewriting upwards, rewriting whoever was using that thing. So if you think about it, at the point where you are in fact instantiating the thing that you are injecting somewhere, at that point, that is also something, right? That is also an object. That is also part of some kind of class. If that isn't injected, right? If that's injected, you just move up the chain. But if that isn't injected, then you have to rewrite that, right? But again, the rule says don't rewrite, write a new one, right? So you write a new one of that, of whatever that is, right? You write a new one of that, and then inject that to whoever was using that, right? So it's kind of a question of dependency injection into methods. I've tried this out for some time now. It's entirely possible. It's completely possible. When you want to change something, right? Simply write a new member, find out where you need to inject that new member, and yes, then I would pragmatically say, like, if that rewrite doesn't cause, if I'm sure that that doesn't cause any interoperability conflicts, right? Any conflicts with other pieces of code, then I would simply rewrite that. But if I can't rewrite that, then I would definitely go up the chain and say, okay, let me write a new one of these things where using the thing I just wrote the new thing for, right? Then write a new one of these as well, and then upwards. Or let me write a new one for that, and let me write a new one for that, etc., etc., etc. Until you have sort of a new main wrapper for your application, right? But at some point you can probably stop and say, okay, pragmatically, I have enough control of this piece, so I don't need to rewrite upwards, I can just rewrite here, right? But that would be a significantly safer rewrite than rewriting the small pieces down in the application. So to sum up, I think it's entirely possible to avoid rewrites altogether. You can simply get along with only writing new code and deleting old code. And then I don't mean as in deleting a chunk of code, I mean as in writing a new modular class and deleting another modular class. That's it. Thanks for watching, and I'll see you in the next one. If this was super confusing, by the way, please let me know in the comments so we'll get further into this. Today I want to quickly talk about command query separation in relation to events. I've done a previous video on command query separation, so if you haven't checked that out, be sure to check that out. But very shortly, command query separation is about separating your methods that perform commands from your methods that perform queries. Any method that mutates state is a command method, and any method that returns a value is a query method. So command query separation asks you to separate these two, so that some methods are not both commands and queries. In other words, they are not mutating state and returning values. To really get a quick grasp of what it's all about, think about this quote was formulated by the person who formulated command query separation. Asking a question should not change the answer. But there are some edge cases that make separating commands from queries difficult. One famous example is the pop method on a stack. So if you call pop on a stack, you remove the first element, but you're also returning that first element. So in some sense, you're performing both a command and a query, and then in some sense, you're then asking a question that does change the answer. But let's back up and talk about a simpler scenario. Imagine that you have an instance of a user and you call save on that user, and then imagine that when you call save, that user is then saved to a database or to memory or whatever. Essentially, it mutates some kind of state, but it does so synchronously. So in this hypothetical example, when we call save, yes, the user saves, but also if the user was unable to be saved, you get an error message back. So in other words, imagine then that you want to do two things. You want to save the user, i.e. mutate state, i.e. command, but you also want to know whether the save was successful. You want to return something, i.e. a query. So let's say that would be returning a boolean, for example. That would be a trivial scenario. If we make the scenario a little bit more complex, then you could say instead of getting back a boolean, you get back a string that contains the error message, right? So it's kind of obvious that we're doing two things. We're saving the user, but we're also returning some kind of value that describes whether the save of the user was successful or not. So if you think about that, the scenario is actually very, very close to the pop example, the pop on a stack example. It's essentially the same problem. Instead of doing two things, we are doing both of them at the same time. So I found a very interesting Stack Overflow post on this particular topic, and I'll link that in the description. Because an obvious way of mitigating this problem is, of course, to mutate the user object with whether the save was successful or not. But that just doesn't really feel right. I can totally relate to that feeling a bit awkward, right? Because then you call save on the user instance, and you mutate the user instance to contain whether the user was saved or not. So when you then want to make a decision further on, you would have to inspect the state of the user in order to determine whether to try to save again or change the kind of value of the user, or whether it actually successfully saved. But to get to the point, essentially, events are another way of trying to mitigate this issue. So just as a parenthesis, of course, there are many, many ways of solving this scenario. And there are many ways of solving this problem that does adhere to command query separation. Events is just one example, but I find it particularly interesting. So let's talk about observer pattern rather than events, because I think that's sort of a more universal way to talk about the same concept. So observer pattern or event essentially sort of invert the control flow. Instead of pulling data, you push data, right? Instead of clients pulling data from a server, the server pushes data to the clients. So observer pattern in a nutshell, remember. Observer pattern consists of a subject that can be observed, in other words, an observable, and a bunch of observers that register to the observable, and then are notified whenever the observable undergo changes that observers might be interested in, right? Same thing as events, right? You register an event handler that listens to a particular event. So when an event occurs, you want that particular procedure or method or whatever to be called and executed. So if you think about that, right, that inverts the control flow in the sense that instead of checking and asking whether it's time to perform something, you let the other person, you let the server, you let the other thing determine when it's time to call that particular procedure. And if you sort of think about what that means that we move from a query to a command. And that's the essence of trying to use events to adhere to command query separation. So in the particular scenario we talked about before with the user, this is what we could do. We could move to events and push commands rather than pull data through queries. So if before we call user.save, register an event handler, or in the case of observers, registers an observer that observes saving of, say, users, or hypothetically something more general. But essentially, we register an observer that is interested in knowing whenever something was saved. Or if you think about error handling, that gets notified whenever there was an error trying to save something. So this means that when we call save on the user, we don't actually have to get a value back, right? We just send the command, save this particular user, and if that saving for some reason fails, then that save method can simply dispatch an event that says that there was an error saving this user, right? So instead of returning that back, right, instead of turning the method into query, we keep it as a command because it dispatches an event that says there was an error saving this particular user. So it dispatches a new command, right? So it's a chain of commands. So that's why I say it's inverted, right? So instead of calling the method and getting a value back, right, we call the method and then dispatch another event that invokes a method in a place where we can handle the fact that some users are saved and some users are not saved. Or we can handle the fact that sometimes we get errors when we're trying to save users. So to sum up, the key lesson is, when you have something that is both command and a query, and you want to adhere to the command-query separation principle, perhaps what you can do is to dispatch an event rather than to return a value. In other words, removing the query portion from your command query and simply turning it into a pure command that dispatches another command. i.e. dispatch is an event that somebody else can listen to and act upon that. And I hope you can see how this can be used to solve the aforementioned pop problem on a stack. Thanks for watching, and I'll see you in the next one.
Hey, you want to get leaner, stronger, learn some cool calisthenics, bodyweight skills, but right now you may need to apply some extra weight first.
So I think I'm getting a handle. So let's talk about the differences between mockist style testing and classicist style testing. Or expressed as isms, mockism versus classicism. There's a great blog post on the blog The Agile Warrior, and I'll link that in the description. But I just want to give you a few quick points. The main difference between classicism and mockism is whether you are dealing with real objects or whether you are dealing with mocks. Kind of intuitive given the name, right? So when you're testing a unit and you're doing classicist testing, then you allow that unit to collaborate with all of its dependencies. But if you're testing that unit in a mockist way, then you mock all of the immediate dependencies. And because you mock all the immediate dependencies, you don't have to mock deeper dependencies, assuming that your system under test doesn't violate the law of meter. Because in the latter case, you may have to mock deeper members as well. But if you're not breaking the law of meter, then you should only have to mock the closest members of the thing you are testing. Or let's say the closest collaborators of the thing you are testing. So let's get very concrete. Think about it. Say that you have a duck class, and the duck class has a greet method, as in a greeting. So the greet method takes another object, and that object may also be a duck, but the assumption that we make, let's say that we're in dynamic language so we don't have types, but the assumption that we make is that whatever is passed to the greet method of the duck responds to name and responds to origin, say. So origin as in like, where does the thing or where does the duck come from? And so what does the greet method do? Well, the greet method does this. If you have a duck and you give the duck another duck, and let's say that this duck is from Canada and the name's John, then the first duck who's past the John duck simply says, hey, John from Canada. If the duck is past another object, say Jane from Sweden, then the duck says, hello, Jane from Sweden. That's it. Nothing strange. The point is that we have a collaborator, right? The point is that the greet method is not a leaf in the object graph of the application. The method has a dependency. It takes a complex object. It does not take a primitive. It does not only collaborate with primitives. So this means that if you're doing classicist testing, then you would write a number of test cases where you pass a real instantiated duck, not a concrete duck, to the Greek method. So you're allowing the method to interact with real dependencies. But on the other end of the spectrum, if you would do mockist testing, you would say, but why is it important what the collaborator of a duck is? What actually happens is that the method makes an assumption about interface of the thing it is passed. It's like duck, right? So the duck is passed something that quacks like a duck. It's passed something that responds to name and responds to origin. So if you're doing mockist testing, then you would simply pass a mock that responds to those particular methods. So I think the aforementioned blog post captures this quite nicely when he says that the classicist approach tests states, whereas the mockist approach tests behavior. Because since we're mocking members, remember that we're mocking a duck, then it only actually knows how to do naming and how to do origining, right? How to respond to name and how to respond to origin. It doesn't know any of the other things that a duck potentially might also know. So we're coupling our test to that interface in some sense. So in mockist style testing, we are testing whether the duck delegates to this mock correctly. In other words, delegates to its collaborator correctly. And there's a strict interface, there's a strict definition of how it needs to interact with the collaborators. And this is why I say couple, right? So there are pros and cons of this. Before we go further, let's also consider what happens in the classicist case. Again, then we are focusing on states, not on behaviors. So the thing in the classicist case is that we are not testing delegation. We are simply testing output we get back given a certain set of inputs. Assuming that the method in question is not mutating, right? Because then we would have to inspect the state of something else. But if it's a non-mutating method, if it's a query method, if essentially this read method returns a string, for example, rather than prints it to string. So in the classicist case, we would be testing whether the string we get back is correct only, right? So we're coupling, back to the coupling discussion, we're coupling in some sense less than in the mockist style, because in the mockist style, we're potentially, if we want to, both checking the output, but also definitely also checking the delegation, right? Because we have a mock and we make expectations whether the thing we are testing is interacting with our mock appropriately. So I think if you understand that sort of captures the essence of the difference between mockist style and classicist style. So there are a number of advantages and disadvantages with both approaches. So again, as we talked about, coupling is higher in the mockist style. But on the contrary, as J.B. Ritzberger talks about in his great talk, Integrated Tester Scam, I'll link that as well in the description, mockist style testing brings you closer towards checking rather than testing. In other words, closer to verification, to general verification rather than case-by-case testing. So in some sense, that would give you greater security in terms of how confident you can be that your system actually works, and not that just that you identify few cases that actually work. So in that video further, he makes the argument that classicist testing is unreasonable because if you have to integrate with the dependencies, then essentially it becomes a combinatorial problem. You have dependencies that have dependencies that have dependencies, etc., etc., etc. And if you do the calculations, you'll see that there are just an insane amount of tests to write if you actually theoretically want to cover all of the cases. Now, of course, all cases are not always relevant, so you may apply some heuristics and only test some of the cases. But still, I think that's a profound point in how easy it is to think that we are testing more cases than we actually are. But I digress, so let's cut this off here. Let's take the extremes. Mockist style, mock everything. Classicist style, mock nothing. Thanks for watching, and I'll see you next time. Every occurrence of a breach statement can be replaced by Examples of high-level iterators are map, reduce, filter, find, reject, etc., etc. If you're familiar with these statements from before, I think you'll know exactly what I'm talking about. If not, I highly suggest that you simply start by looking up map. I have a screencast outlining maps, so I'll link that below. So I briefly talked about the topic covered in this video, but I wasn't really satisfied with the way that turned out. I was too focused on map, and I was too focused on the benefits of readability. So I'd like to get another shot. So what is the argument? The argument is that in all places where you're using a for each, you could instead be using a high-level iterator. So I came across this interesting Stack Overflow answer. I'll link the answer in the description below. But that person seemed to argue that the reason why it's generally a good idea to replace the sort of procedural counterpart with a high-level iterator is that you are seldom interested in only iterating over the collection. What do we mean? We mean that you are usually interested in aggregating or constructing some kind of new value and then returning that new value, rather than simply merely iterating over the collection. If you think about it, that makes a lot of sense. I mean, why would you iterate for the sake of iteration? But what are these cases when you're not actually interested in returning something? Here, I think it becomes super helpful to think about command query separation. I've got another video talking specifically about command query separation, so do check that out. But very shortly, command query separation is about separating your methods that perform commands from your methods that perform queries. Queries in this case are methods that return values, whereas commands are methods that mutate state. So if you think about this, you'll realize that all of your query methods are returning something. So if your query method consists of some kind of iteration, then likely you can return something directly from the iteration. It's a query. But command methods, on the other hand, they are mutating state. And this might actually be a valid reason for not using a high-level iterator that actually returns a value. You could simply use the classic for each construct, or use the high-level version of, or the high-level iterator version of the for each construct. So if you are not already separating your commands from your queries, then this transition into high-level iterators might not be as smooth as we are describing here. But if you are already separating your command methods from your query methods, then this transition into high-level iterators will definitely be easier for you, almost trivially obvious, right? You simply identify whether you have a command method, and if you have a command method, you use for each, or you use the high-level iterator version of for each. And if you have a query method, then you use another one of the high-level iterators. That's it. Thanks for watching. High-level iterate, or use the high-level version of, or the high-level iterator version of for each. Let's talk about the difference between checking and testing. Both deals with determining whether the program is correct, whether it behaves according to specification. However, they do so in slightly different ways. Think of it this way. Checking checks the general case, but testing tests specific cases. Or in the case of a single test, a test tests a single case. This means that when it comes to how certain you can be about your programming working correctly, you can be more sure when you have checking, or when you are performing checking, rather than when you are performing testing. But let's unpack the previous statement about checking general case and checking specific cases. If you're doing design by contract, in other words, you're using preconditions, postconditions, and invariants, then you are checking. You are logically inferring whether the program is correct. You express what the program is supposed to do in the general case, and let the static checker analyze your program to determine whether your program actually does that thing. Or perhaps more accurately, whether your program certainly does not do that thing. Or perhaps even more accurately, whether there exists a case where your statement about the program cannot possibly be true. So if there is a case where your program doesn't work. So this is all checking, right? Checking the correctness of the program, logically, generally, making sure that it behaves according to specification on a general level. So let's not talk about testing instead. Testing does not check general case, but rather a specific case or a series of specific cases. So it's a proxy for testing the general case. So instead of testing the general case, we test a series of specific cases and hope that that will saturate the tests enough, will give us enough information so that we confidently can say that that the system probably works. In checking, we can theoretically be 100% certain that the program actually works. In testing, even in theory, we can't be 100% certain without actually enumerating all of the possible scenarios. In other words, figuring out and testing all of the specific cases, which usually we don't because of cost benefits. At some point it sort of becomes absurd. So when we talk about testing, we generally refer to testing and not checking. When we talk about unit testing, integration testing, etc., then we talk about testing, not about checking. But the reason I wanted to highlight this distinction and this discussion is that people like, for example, J.B. Rainsberger have argued that in the discussion of mockist-style test-driven development and classicist-style test-driven development, that if you are doing mockist-style test-driven development, you can actually move closer towards checking and further away from testing. We'll discuss this specifically in another video and in detail in another video, but just to give you a glance, just think about it. If you are injecting mock members and checking that your code is delegated to these mock members appropriately, you are then no longer just checking input versus output, but you are also checking delegation. So you're checking input, that delegation is handled properly, then output. So in some sense you are checking whether the pieces of your application are correctly composed together, which moves you closer to the land of checking, because you can talk about that even in a testing world in the general sense and not just in specific cases, in terms of specific cases. So again, checking checks the general case, testing tests the specific case or a series of specific cases. Thanks for watching.
So I've got my essay written, and I've been working on it for about a week. So now I'm going to show you how I use Grammarly today.
In the book Refactoring by Martin Fowler, the author, tells the story of him and Kent Beck when they're on an airplane. So Kent Beck is usually denoted as the father of XP, the methodology extreme programming. And as the story goes, they are pair programming on this airplane. And Martin Fowler says that this is sort of the first time he really in practice comes in contact with the idea of using the pieces that are outlined in the book. In other words, judiciously following rules, refactoring code by performing those small pieces of actions in combinated series. So what I wanted to quickly talk about is that idea. If you haven't read the book Refactoring, it's essentially a cookbook of refactoring recipes. Remember, refactoring is the idea of re-architecturing code, rewriting code without changing the behavior of the code. The program stays the same, but you've rebuilt it in a different way. The idea behind this is, of course, that you would try to maintain the architecture of your application to, let's say, keep it healthy. So I would guess that most of us believe that refactoring generally is a good idea. However, I would also guess that many of us recognize themselves in that refactorings are not always easy and can many times be painful. Painful for you, the performer of the refactoring, and painful for potential colleagues who have to wait for you to complete your refactoring. So previously, I myself have viewed refactoring as something that you enter, and it will take a long, long time before you fully exit. Because the nature of refactoring demands that you stay in the refactoring for a long time. Let me be more specific. If you follow the way that Martin Fowler uses the term refactoring, refactoring does not mean a massive rewrite in a single pass, in a single go, and in a single session, or over a consecutive series of days without ever performing a commit. Rather, refactoring means to incrementally move the system towards a healthier state, to take small, healthy steps that bring your application towards a better direction, towards a better architecture. But at each of these small steps, the code base is still functioning, the program is still working, the software can still be delivered. And this is the key point. So back to the blame story. The way I understand it, it seems that Martin Fowler is saying that that's the first time when he really felt that, Kent Beck, when they're pair programming in that session, is actually taking small, deliberate, controlled steps when rewriting his code. He He's not saying, oh, I've got this great idea of a superb architecture. Let's rip out all the pieces and try to stitch everything back up. It seems he implies that they know the futility of that kind of behavior. They know how often you instead end up in a situation where you're failing to stitch the pieces back together, or where your idea of where you were going turns out to be a bad idea, and then you simply fail out halfway. So while I would highly encourage you to read the book Refactoring, as even though it talks about things that are very familiar to a lot of us, it gives us names to things, which mean that we can talk about them, and in discussion with other programmers, we can be less ambiguous about what we're meaning. So if you would say extract method or extract class when you're pair programming with someone, that person would know exactly what refactoring you're referring to. And perhaps even more importantly, they would know that you mean a certain set of steps, but not anymore. So it's not that you're implying that you would perform a larger refactoring. You're just saying, okay, let's just start, or at this step, let's just do extract method and see where we should go from that. Right? You can still have an idea of what you want your architecture to look like in the future. You can still have a grandiose idea, but it's important to take that small step to put yourself in a new state where all the tests are passing and the build is passing, and you can actually ship the software because you haven't broken it. You just refactor a very small piece of the application. So again, while I highly recommend that book, let me give you a short, more concrete idea. This is something I've been thinking about lately. Perhaps a way to approach refactoring is to have that idea of where you want to go, right? I mean, it's I guess as programmers, at least for me, it feels inevitable to think about that grandiose architecture where I'm trying to go, right? But refrain from ripping out multiple pieces and aggressively moving towards that design. Instead, ask myself the question, what is the smallest change I can make that helps me make the next change towards that big change easier? Right? It's kind of like that saying, when you perform a change, make the change easy, refactor the system so that the change is easy, and then make the change. Kind of similar to this, right? When you have an idea of a better architecture, instead of aggressively moving towards that, ask yourself, what is the smallest step I can take that puts my application in a state where it's easier to perform the next change or another change that moves me towards that final state that you're looking for. What I've found especially interesting about an approach like this is that I often find myself in a situation where I embark on one small step, and as that step unfolds, as I try to perform that refactoring by, you know how when you rewrite something, you cascadingly have to rewrite dependencies. So as you embark on the journey of rewriting dependencies, I may realize that I'm suddenly rewriting a lot of stuff, which makes me a bit uneasy. So I stop and I step back and I say, okay, wait, if I look at the pieces that I've now refactored, is it possible for me to, instead of doing it the way I'm currently doing it, find one smaller piece in the set of things that I'm doing currently and refactor only that thing and then commit, right? Put that into source control. So that often results in me throwing away the changes I've made, right? Or it's stashing them so that I can peek at them to look at sort of where my thinking went. But definitely throwing it away and starting over and doing only that small thing. Because if you think about your application tree, it might be natural for you to start at a branch when you're refactoring. But then as you're digging down that branch, you realize that branch have a bunch of sub-branches. And suddenly your refactoring is bigger than you were perhaps intending. And at that point, you can probably locate a sub-branch further down the branch you wanted to refactor and refactor only that instead. So that I found to work extremely well, because then you are refactoring in small steps. You can commit in one change and then sort of take your mind off of that piece because you know that that piece is working, which also reduces the size of your ifs and reduces the size of your commits, which at least makes me more at ease. So when you're refactoring, ask yourself the question, what is the smallest change that I could possibly make that would bring me closer towards a state where the next change I want to make is easier when you're moving towards a greater refactoring? If you're used to doing something similar, feel free to outline that in the comments, as I am. I am sure that others would massively appreciate it. That's it for today. Thanks for watching, and I'll see you in the next one. I previously argued that abstraction equals pragmatism. That to abstract when you're programming actually is to be pragmatic. To get an in-depth argument, I'll link the videos where I talk about that specifically below, so be sure to check that out. But the short version is that there always seems to be two sides to this argument, where people argue that on one hand, there's the notion of premature abstraction, essentially arguing that to increase the abstraction of your system before you actually know why you need the abstraction means that it's likely that you'll end up in a situation where you didn't actually need the abstraction at all, because you misunderstood the need for the abstraction. Or there's the saying, you will never know as little as you know right now. You're anticipating change that will never actually come, which is why people argue that it's premature and that you should wait until you have the need for that change and then abstract so that you can get that change into the system. It's the same. I think it's Kent Beck who said something along the lines of that when you need to introduce a change to your system, change the system so that the change is easy to make. And the parenthesis to that changing the system in that way might actually be the difficult part. But the point is essentially that you should refactor your system to a point where the change you want to make is easy to make, instead of crowbarring the change into the current architecture that you have in your system now. Anyways, so there's always these two sides of the story. People like me who perhaps lean a bit more towards the argument that if you increase abstraction now, you will have a more flexible system so that when you are hit with change requests, it will be cheaper to change your system. And that the cost of introducing these abstractions now aren't actually as severe as people may argue that they are. So I'm particularly fond of the idea of pivoting, essentially meaning that we seldomly understand the business value or the actual value of our software before we thoroughly engage with users and sort of evolutionarily realize what the value is and sort of pivot our application towards where the value is. So in order to keep ourselves as flexible as possible, in order to keep ourselves as able as possible to pivot towards where the value seems to be lying, we need to increase abstraction. Right? If we're locking ourselves into a corner where we can change the system, well, it's difficult or it's expensive to change the system to pivot towards where the value seems to be, which means that our competitors will be quicker, potentially, in pivoting towards where the value is, and it's difficult for us to maintain our same market share. But that's all stuff discussed in the other videos. Let's get back to this topic. What I want to say in this video is that I came across an argument by Sandy Metz, and I think she puts it in a better way than I do. So the way I understand it, she's more on the pragmatic side of this argument. She's more on the side of saying that it's very, very important that we're not prematurely abstracting, because that essentially means that we're going to incur a lot of cost that actually doesn't give us a lot of benefit later on, and that it's very likely that we anticipate the wrong change. But essentially, she says this. She says that when your requirements are clear, do not introduce abstractions that are not necessary to solve the immediate problem. In other words, when your requirements are clear, solve the immediate problem. Do not anticipate other things. Solve the problem that you have right in front of you. But when your requirements are not clear, you should introduce abstraction. You should increase the level of abstraction so that when your requirements become clearer, it's easier to move towards that. You're not locking yourself, you're not walking into the wrong corner. So how would you know which requirements are clear? She seems to think of it this way. So like, if when you're talking to whoever is giving you the requirements, if that person, if your client, is very specific on some things, it's very easy to get specific answers from the clients, then that means that the client have a very good idea of that particular requirement. If the requirement becomes very elucidated, very clear, very, very sharp, right, then stick to that. But when you ask penetrating questions about a particular feature or about something very specific, and the client starts to get vague or starts to deliver conflicting information or anything like this, then you should take that as a warning signal that maybe it's that the client don't actually know where the value lies, what software they want to have built, right? Which is not to blame the client in any way. That's completely natural, and again, it makes sense because we have sort of a hunch about what we want to explore, but we're not super sure where the value lies. We're not super sure whether we should do it exactly this way or exactly this way, right? But again, whenever you find yourself in those situations, facing those kinds of requirements, deciding upon one of the very specific explanations that the client gives, and then implementing that, and then locking yourself into that corner, locking yourself into that room where it's very costly to get out of that particular solution later. You should instead, for sure, lock yourself into one of them, but increase abstraction so that the cost of changing the specific solution later on is not super expensive. And perhaps I think it makes more sense to think of it this way. So Sally Metz seems to argue that you should ask yourself the question, if I'm misunderstanding what they're saying, or if they change their mind about this later, which seems likely because they are giving conflicting information or they're being vague or etc. What would be the cost of changing this later on from a software perspective? Right? How expensive would it be to change this later on? If it's not expensive, then never mind. There's no need for that abstraction. There's no need to increase abstraction because the change is going to be cheap anyway. But if the change is going to be costly, that's when you need to increase abstraction. I think it makes perfect sense, and I think you should follow this over what I've been saying about abstraction always equaling pragmatism. So let me revise that. Abstraction is always pragmatism when your requirements are not clear, and when it's expensive to change your mind later. Abstraction is pragmatism, but only if you don't know exactly what it is that you're building. If you know exactly what it is that you're building, then maybe you don't need abstraction, because you're not actually anticipating change. But as soon as you're anticipating change, and it would be costly to implement that change without abstraction, then introduce abstraction. Here's something very trivial that I still find quite interesting.